Hello everyone. Today we're going to talk about zero-knowledge protocols. This is one of the most intriguing and fascinating topics in cryptography for multiple reasons. On the one hand, its philosophy made precise the notion of knowledge and of lack of knowledge being somehow formalized in a mathematical and computational way. On the other hand, there's so much interesting mathematics in the protocols themselves. And finally, this is seeing quite a lot of exciting new applications like in cryptocurrencies and many other places. This area was created by Goldwasser, Micali, and Rakoff in this paper called The Knowledge Complexity of Interactive Proof Systems. Some years back, Goldwasser and Micali received the Turing Award, which is computer science's highest honor, for general contributions to the foundations of cryptography, including, as one of them, the development of zero-knowledge protocols. The setup is two parties who are exchanging messages. One is called a prover and the other is called the verifier. There is some claim made by the prover. I here stands for instance. The prover may also have a secret associated with that claim. On the basis of knowledge of this secret, she's claiming that this is true, or even that she knows or possesses a secret that makes it true. And she wants to convince Vic of this. And this conviction will take the form of interactions in which she sends a message, Vic sends a message back, and so on, until in the end, Vic outputs a decision, which is a Boolean. The purposes of the protocol are twofold. First, that the prover should convince the verifier that the claim is actually true, and possibly that she knows the underlying secret or witness. The zero-knowledge aspect is that nothing beyond that should be revealed. So nothing about why the claim is true or what exactly is the secret that makes it true. Here's a few examples of that, of domains where you might be interested in something like this. Some more mathematical, some more esoteric. So for example, suppose you're simply talking to another student and you claim that you know how to solve the homework problem, which was pretty hard. And the other student says, yeah, I don't believe you, show me the solution. But you don't want to give away the solution. So you just want to brag. So how do you do that? Well, you can give a zero-knowledge proof that you have this solution. In a more applied context, we often authenticate ourselves to websites by flowing our passwords to them in the clear over TLS. You could also imagine that you simply prove in zero knowledge that you have a valid password. The advantage over the normal solution is that even the server doesn't actually need to know or ever acquire your password. People have discussed how if you find the proof for a long-standing mathematical conjecture, like P is not equal to NP, you want to claim a prize. The Clay Institute is a institute that's named a number of what are called Millennium Prize problems, and they've given an allocation of $1 million to whoever solves any of them. So if you have such a proof and you want to make the claim, you may be worried that someone will copy your proof and claim that it's theirs, so you don't want to publish the proof very publicly. So instead, maybe you approach the Clay Institute with a zero-knowledge proof that you have this mathematical proof. We're going to start illustrating how you might do this with a kind of a story-based example, a non-technical one, which builds on the story of the classic Arabian Nights tale of Ali Baba. Now, it turns out that this is used in a bunch of places to explain zero knowledge, but I didn't always find it to make a lot of sense. And Joseph Yeager, who was a TA for this class a few years ago, helped out with that. And so I'm going to use his variant or version of the protocol, which I think is more meaningful. So as per the story, remember that it's about there being some kind of portal with a door, and there are some magic words that allow you to open the door. If you speak these words, the portal opens. And the way we're going to look at it is that the portal is two-sided. You can go from either A to B through it or from B to A. And the magic words corresponding to those two directions are different. So there's a certain secret you speak to go from A to B and possibly a different one to go from B to A. Now Peggy has one of these secrets, and what she's going to do is prove to Vic that she has one of them, but Vic is not supposed to learn which one. Or putting it another way, Peggy is going to either prove she has the ability to go from A to B or the ability to go from B to A. But at the end of this, all Vic knows is she can go across the portal, and he won't know in which of the two directions she's actually capable of going. So how does it start? Well, here's the sort of physical setup. This red bar represents the portal, and A is this side of it and B is this side of it. This represents some kind of wall, and you can't see through that wall. So what Peggy starts by doing depends on which of the two secrets she knows. Let's suppose that she knows how to go from A to B. So then she's the first person to enter the cave, and she goes and just positions herself here next to the A part. Now notice that given this wall, no one can actually see Peggy if they're sitting over here. Now that Peggy is in position, she tells Vic to enter the cave, and only now does he come in, and he sits at this point. He can't see Peggy. What's he going to do? He's going to give her an instruction. He's going to say, please appear at location C, where C is either A or B. He picks that at random, which of the two it is. Now, Peggy responds by obeying this command. What she does, though, depends on which command Vic issues. Let's say that he says appear at point A. This is very easy. She just walks right out of here. And Vic, of course, knows what's A and what's B, and he just sees her appear here and says, okay, you did it, you came out of point A. What if Vic had said appear at point B? Now, in general, it would be kind of hard to do because you have to get across this portal, which is very difficult in general. But Peggy happens to know the magic words for A to B. So if she's asked to come out at B, she whispers those magic words, and that allows her to get through and come out here. So again, Vic says, well, great, you managed to appear at the end I asked you to. Okay, so far, what have we got? We've just got that Vic issues a question and Peggy answers it 100% of the time correctly. We start seeing a little bit more about what's going on when we consider the other case. What if Peggy knows how to go from B to A rather than from A to B? And what we're looking at is, how does that change what Vic sees? Well, if that's the secret that Peggy has, what she's prescribed to do at the start is to position herself at B. At this point, Vic hasn't even entered the cave, and she's sitting over here. That's different from what she would have done had she known the other password. Then again, she calls to Vic, come in. He comes in, and he sits here. He can't see where Peggy is because of this barrier over here. Just as in here, he says, please appear from either A or B, where I'll pick that choice, call it C at random. Of course, Vic is doing the same thing here as here. He has no idea in which situation he is. It's only Peggy who knows the difference. And now we claim that Peggy can again comply. Why is that? Suppose the request was to appear at point A. Well, in general it may be difficult, but luckily Peggy knows the magic words to go from B to A. So sitting here, she crosses over and then walks out here. And Vic says, oh, I see you appearing at A. Now notice that from Vic's perspective, whether it was starting here and getting here or starting here and getting here, it looks identical. All he sees is, I told Peggy to appear at A, and lo and behold, she did. Now again, in this case, if he says appear at B, she can do it quite easily. She doesn't even need any magic words, just walks out from here. Again, from Vic's perspective, he has no clue whether that arose from this situation or this one, because in both cases, all he sees is Peggy walks out at slot B. Okay, so now we're going to discuss in what sense this has properties that we're going to think of as being associated to zero knowledge. It turns out that it isn't one property we're interested in, but a whole slew of them, and somehow the non-triviality or interest only emerges when you have all these properties. The first one is trivial, but it's still important, and it's kind of the equivalent of a correctness condition in a cryptographic primitive. It just says that suppose everybody's honest and doing what they're supposed to do, then the verifier will always accept. In other words, suppose Peggy's claim is true, meaning she does know one of the two passwords or magic words. Then if she and Vic both follow the protocol doing exactly what's instructed of them, pretty much as we saw in trace through, the verifier will always accept, because he will see Peggy emerge at whatever side he wants, regardless of which magic word she knows. Okay, now the other condition is, what if Peggy's claim is false? And this is why we talk of the notion of a proof, meaning she actually doesn't know the magic words. She knows neither of them. She's just trying to fool Vic by claiming that she knows one of the two magic words. Now, she will be able to succeed in fooling Vic, that's about half the time. But the fact is, what the protocol ensures is no matter what, no matter how she tries to behave, as long as Vic does the steps he's supposed to do, Peggy can't win with probably more than a half. Now, when we think about this situation, Peggy is no longer an entity doing what she's told to do in the protocol, which is, if you know this, go here. If you know this, go here. Because in any case, she doesn't know either magic words. Where she goes is entirely up to her. We don't know anything about it. And we think of her as an adversary. She starts at whatever position she wants. However, what happens is when Vic says appear at some point A or B, chosen at random, there's only half probability that she can do that, because with probably half, it's the other side of wherever she is, and she doesn't have the magic words. Now, you may think that fooling Vic half the time is too large. That's true, but then we can just repeat the protocol to get it down. And finally, the knowledge aspect. Why is this zero knowledge? Well, because assume again now that Peggy is honest and her claim is true, meaning she does know one of the two passwords. What we're wondering is, does Vic figure out which of the two Peggy knows? Does he learn whether she can go from A to B or from B to A? And the answer is not. Why? Because look at what he sees. All he sees is that if I ask Peggy to appear at A, she does, and if I ask Peggy to appear at B, she does. He has no clue from which end she's starting. All right. So one of the summaries from this is that there are these three properties that we'll be wanting to look at, and we will look at those many times for many different protocols, and all of them have kind of different setups. The protocol is a bunch of steps we're telling parties to follow. Sometimes parties are adversarial, which means they won't follow those steps. In completeness, the prover Peggy's claim is true and she's honest. And then the honest verifier is supposed to always accept. Soundness says that the prover's claim is no longer true. The prover is an adversary trying to convince you of a false claim. And that means that she's cheating in the sense that the prescribed protocol steps need not at all be followed. Nonetheless, the verifier should not accept with probably at most something, which in this case was a half. In the zero knowledge claim, we're back to saying that the claim Peggy makes is true and she's honest. But now we want that the verifier doesn't get any information beyond the fact that the claim is true. In this case, it means that he doesn't learn which of the two secrets Peggy knows. Okay, so that was a very sort of intuitive description, and it's appealing in some ways. You can get some idea from it of what's going on. But at least I personally also find that if I poke at it more, parts of it don't make a lot of sense. And for that to change, we need to look at things more mathematically. We need to actually have precise definitions. And then based on that, we can assess particular protocols. And beyond a means to assess protocols, definitions are kind of intriguing in their own right. Because think about what one is trying to do. One is trying to say, how do you mathematically capture the idea of knowledge? How do you measure how much knowledge one party, Vic, has learned by interacting with the other? How do we talk of that knowledge being zero and things like that? So there's some interesting things to get into. Now, it turns out that there's many such sort of little examples that are fun to look at. So for example, here's another one, which is a Halloween problem. So it talks about zero knowledge protocol in general, and then it says, look at Alice and Bob, who got some chocolate bars for Halloween, and they would like to know if they received the same amount of candy without disclosing their number of chocolates because they don't want to share. Okay, and then it goes through a protocol. So there's some limitations and interesting discussion, but it's fairly similar to what we saw and quite interesting.